So homework number 5 is due today. And I've been emailing back and forth about some questions with some folks, and I wanted to, and I sent this hint around, I don't know, the other day. But I just wanted to maybe go over with this idea with you because there's still some confusion here. So this is for question number 4, where we want to show that this equals either 0 or 2 pi is what we're being told in the, or pi, I'm sorry, we're being told in the problem itself, in the question. And so we want to show that this equals 0. Let me double check what it says. 0 if n does not equal m, and it equals pi if n equals m. That's what we're trying to prove here. And so we start with the inner product. The inner product is the two things multiplied from minus infinity or minus pi to pi. And then what we had seen in page 2 of the notes from this section was this formula here. This is lemma 5.1. I know it's not labeled here, but it's labeled in the text. And so this tells us what the integral, so first of all, this is how we can relate sine and cosine to e. And then this tells you when you integrate this weird version of e, what happens when you integrate it. And so we know that this is true. This is something that we're given. And so that means if we did, put an nx and an nx in both of those and an mx, it would become this expression. And then when you distribute all those things, right, because this is like something you would need to distribute, you would get this expression. And again, we want to show that this thing equals 0 or pi, depending on if n equals m. And let me first start by saying that you've got 4 terms being added together here. It's 4 different e terms. And so you can break this integral up into each one of those things separately. And then each one of those things separately, you can just use this theorem to tell what happens. Right? And so in this problem, if m equals n, then e to the I m minus n just becomes e to the 0. And if you have e to the 0, this tells us that if you have a 0 up there, the answer is 2 pi. And so if I integrate this, you get 2 pi by lemma 5.1. And the same thing will be true with n minus m. And the other ones, you're doing 2 cases. You're saying, suppose m equals n, then this happens. And then you do another case where you say, if m does not equal n, then something else happens. And those are the 2 cases you're trying to show. You assume they are not equal and you show something happens. And then you assume they are equal and you show something happens. There's 2 separate cases to consider. So if m equals n, this one ends up being 2 pi. The other one is going to be by the theorem equals 0 by lemma 5.1. And you do a similar thing with m not equal to m. Right? If m is not equal to m, and you look at this, then this is not going to be 0. And lemma tells us that this is going to be 0. So you don't need values for m and m. You don't need to actually do any integration. You just follow the steps that I'm sort of laying out here and use lemma 5.1 to show what the integrals are. And you know what the answer is, right? These are the answers. And so if you end up getting 0 when n is not equal to m, you've done it right. And if you end up getting pi, if n equals n, then you've done it right. And so what should end up happening is there's a 4 here. So you're going to end up doing, right, there's a 1/4 out front. And so when n equals m, you're going to end up with 4 pi over 4. And then it's going to cancel into just pi. Answer some questions about that one. All right, so just to be clear again, because Bradley's asked me a couple times, like, how do you know if n equals m or whatever? If you look at the problem, there's two cases. There's the case where n equals m and n doesn't equal m. And you need to assume one and show that the result follows, and then assume the other and show the other result follows. That's the idea behind this particular problem. What else can I answer right now?
So if n equals m, isn't it supposed to be pi, not 0?
Just put it away. Did I write down the wrong thing?
Yeah, it's supposed to be pi, but
so it would be e to the ix, and then
no, it would be, if m equals n, you're talking about the m equals n case?
Yeah.
Then this is going to end up being a 0.
Why?
Because if m equals n, excuse me, just subtract them over to the other side. Right? Two numbers equal each other, and you subtract them, you get 0.
I thought if m doesn't equal n.
If two numbers are equal and you subtract them, you get 0.
So in the thing it says if n doesn't equal m, then it's 0. If n equals m, then it's pi.
Right. The inner product equals that. So this integral will end up equaling that.
So I'm still confused of what I'm supposed to do.
What you were just showing was just one piece of that huge integral, right? So when n is equal to m, that one piece that you were showing ends up equaling 0, right? But you still have 3 other pieces to do.
Correct. Yeah. So I was just showing this one particular piece. I was pulling this particular one out and showing that one.
Yeah, so that individual is 0, but once you do the rest of them, it should equal pi.
Yeah, so 2 of them will be 0, but then 2 of them are going to be 2 pi.
Yeah, so then
so you end up with 4 pi over 4.
I don't know. I still don't get it, but it's fine.
Okay, you can. I'm happy to work with you outside of it, or you can just you've gotten most of the way there yourself. I'm happy to answer some more questions, but maybe we could do that outside of class. Or if there's someone else has a question about this one, I'd be happy to clarify it. But let me just maybe say one more thing.
Also,
yeah, go ahead.
If n equals m and you get pi, then what do you do with it? Like, can you show me an example if that's the case?
Okay, I guess we're just going to do the problem. So let's assume m equals n. If m equals n, the integral turns into this.
So you just put in a 2 there? Even, okay.
If m equals n, then you're adding them together. Those two things add together to get 2 of them. Right? If m equals n, you're doing m plus m, for example, which would give you 2m. Right? Doesn't that make sense? If you have n plus m and m equals m, then that's the same thing as m plus m, which is 2m. That's what I just did there. And so then the theorem says, I'll put the theorem back up. If you have a 0 up there, if k equals 0, you get 2 pi. If you don't have a 0 up there, it's 0. And so this ends up being 1/4 times, which is which here? 0 plus 2 pi plus 2 pi plus 0, which is 4 pi over 4, which is pi. So if m equals n, that integral ends up being pi, which is what we were trying to show. I know this is kind of hard to see. This says m equals n. Thoughts, Bradley? I clarify that. It's still confusing.
I get it, I think.
Okay. The other one's going to be similar, so you'll just have different versions inside here, basically. I think maybe they... Anyway, I'll let you think about that. Or we can meet again if you want. That's fine. Other thoughts? Other general questions about the homework at all? Okay, I'm going to scan this one up. I'll post that with the notes today. And I'll just mention again that homework is due, I think I put 5 p.m. today. I can't remember, but it's due today. Someone else say something on the chat I missed? M equals n and does not equal 0. It's pi. Oh, Nick was just explaining. Gotcha. Okay, so I do have a couple of videos I want to watch, but I want to just do one more thing with the notes before we look at that video.
You put it in for 2 p.m., so it's not up anymore?
You can still submit it late, I think.
Okay.
It'll just mark it late, but I just won't. I won't pay attention to that. Okay, so we were talking about Fourier series. Fourier series are the way that we can approximate periodic functions. And so we started with this periodic function. That was one period that I had boxed in. And then we approximated that function using an, a0, and bn, and the given function, the given formula, I mean, which is on the previous page, right? We do this. We calculate a0, an, and bn, which are given by these integrals. And then that approximates the function. And then the idea is this is an infinite series, right? And there's n's in here. And so the more of these terms you use, the better approximation we get. That's what we had seen in the last class. And we're going to look at a couple examples today, and you'll have an opportunity to mess around with Maple yourself, and I'm hoping that you'll take advantage of that. But before we do that, I'd like to, there's a couple other things that we should just talk about quickly. Yeah, right. So the first thing is this convergence theorem. And now that we've spent some time on that, we'll see how far we get, but that's okay. So remember, we're talking about approximating a periodic function, little f of x. And previously we had been talking about doing that on a period 2 pi, and we're still talking about that. So around the interval minus pi to pi, right? So this is an interval of 2 pi. And we had said that capital F of x is the Fourier series. So when you see a capital F, that means it's the Fourier approximation of little f. And what this theorem says is that the Fourier approximation is going to equal the function value if the function is continuous at that point. In other words, when you do the infinite series, you will get the exact value at continuous points, is what this is saying. But, you know, we're approximating these piecewise continuous things, right? Like this first one we did, this part's continuous up here, and this part continuous down here, but there's a discontinuity at 0. And so what happens at the discontinuity is what's being told in this second part. The second part, this part right here, is telling us that at a place that the function's discontinuous, the Fourier series is going to converge to the average of the left and the right-hand limits, right? So the f of x plus and f of x minus, those are the things we learned. We saw that notation in the calculus definition section, and we had said that those were the right and the left-hand limits. And so that's exactly what it says right here. Right? In other words, the Fourier series converges to the average of the left and the right-hand limits at points of discontinuity. And so let's look back at that original function, the square wave. The little f in the square wave, if you remember, f of x was +1 or -1, depending on which side of the origin we were on. All right, that was the picture I just showed you. Maybe I'll just I'll just draw the picture too. So this is the square wave. And there's a problem like this in the next homework. So the next homework is due, I think, 2 Thursdays from now. And there's a question that asks you to use this theorem. And so I'm reminding you what the square wave function is. And then also on the square, so I'm just rewriting this right here, right? That's this image. And then what we had seen on that verse example was this was the Fourier approximation of that. So I'm going to write that down too. And so what we had found was the capital F of x, the Fourier approximation, was this infinite sum of this value. So that was the square wave, and this was the Fourier approximation. And so I'm just trying to write that stuff down because the question that we're going to look at here is, let's show that the Fourier series of the square wave converges to 0 when x equals 0. In other words, if you remember the graph we got out of this, we showed it on Maple, and I won't waste our time pulling Maple up, but what Maple did was it created a function where like it oscillated around down here, and then it jumped up to this one and then oscillated around up here. So it did like a nice approximation of those two things. And if you remember, it crossed right at the origin is what happened. And you can see that that's the midpoint between those two pieces. And so this is just a visual showing how that theorem works, right? So the Fourier function actually intersects right at the midpoint. And we can use the theorem to actually show that that happens. And so let's show that the Fourier series of the square wave, which is this right here, above converges to 0 when x equals 0. And then we'll do it also at pi over 2. And so let me just draw that picture right here, so maybe it'll be helpful later. So the square wave looked like this, right? Either at 1 or -1. Excuse me. And then the series kind of like bounced around right here, and then it shot up, crossed at 0, and then bounced around up there. And so let's show, using this theorem, that it crosses it at 0. And so at 0, the function we're approximating, which is given by the Fourier series, the approximation. Oops, I did it. I meant to plug a 0 in. So at x equals 0, f of 0 equals big F of 0. So let's plug a 0 into big F. So that would be plugging a 0 right into the sine function right here, right? And so if we plug a 0 in there, we would get the sum from 1 to infinity of -2 over n pi, -1 to the n plus 1. And then when you do sine of 0 is 0. And so we're just going to be multiplying by 0. In other words, we're doing an infinite sum of 0. And so when you add up 0 infinitely many times, you still get 0. And so this theorem, the Fourier approximation crosses at 0 if we just plug 0 in. And if we use the theorem, we'll also see that. So using the theorem, the above theorem tells us that it's going to cross at the midpoint between the right and the left-hand limits. So f of 0 equals little f of the right-hand limit at 0 plus little f the left-hand limit at 0 divided by 2. In other words, approach 0 from both sides of the line up here. Right? If we approach 0 from the left, we're at -1. And if we approach 0 from the right, we're at +1. And so this ends up being 1 1 plus -1 over 2. Right, when we approach it from the right side, we're at 1. When we approach it at the left side, we're at -1. Those two things cancel. We get 0 over 2, which is 0. And so just kind of showing that this theorem actually shows us that we get the same answer. Can I clarify something about that before we do it at pi over 2? We're going to do, the next question is, what does a series converge to at pi over 2? If we did it at pi over 2, we would do the same thing. We could plug pi over 2 into sine of nx, and then we'll have sine pi over 2x, and so we'd have big F of pi over 2 equals, I'll just cut to the chase and tell you it's 1. It's going to be an infinite series, but I'll just tell you it's equals 1. But instead of doing some infinite series, we could just use the theorem. We could do F of pi over 2 is the left and the right hand limits at pi over 2. And then average them. And if we look at the picture, right, pi over 2 is somewhere here. Pi over 2 is, this goes from 0 to pi, right? So pi over 2 is up here on the 1 part. And so the left and the right hand limits are both at 1 at pi over 2. Right, and so in other words, this would end up being 1 plus 1 over 2, which is 1/2. I'm sorry, which is 1. I meant to say 1. And that makes sense, right? At pi over 2, if we look at the picture, the function is up here at 1. And that's what this is saying. And so instead of trying to evaluate an infinite limit to show that the function gets that, we can just use the point as well. It's not a discontinuity, but the function still, the theorem can still be applied here. And so there is a question in the homework that's kind of similar to this, if I remember correctly. I want you to use this theorem to approximate a discontinuity point in one of the series that you end up finding. So you'll find a series, and then you'll approximate a value using this theorem. Thoughts about that? Questions? Okay. So let's quick look at the next page and remind yourself what Fourier series are and do. And then we'll watch a video to hear about an application. So everything we've done, all the series we've looked at so far, all the approximations are all between minus pi and pi. Right? And if you look at the original definition on page 14 here that I'm about to put up, what we were doing is we were approximating piecewise functions of period 2 pi, and so we were going from minus pi to pi, and that's why all these integrals were from minus pi to pi, and you had like pi's here and all that kind of stuff. The next page is just extending the idea of Fourier series to intervals outside of minus pi to pi. And so this is how to do a Fourier series of a function of period 2L. Okay, and so in other words, we're doing period 2L, i.e. from minus L to L, not minus pi to pi. I mean, minus pi to pi is still applicable here, but we're trying to extend it to other things that are either bigger or smaller than minus pi to pi. And so this has size 2L, where this one has size 2 pi. And so we're incrementally expanding this a little bit to work with more functions than just ones that are between minus pi and pi. And then what I'm going to sort of show you in the video, which I'm not sure we'll have time to get to in the textbook, is you can extend this even further to non-periodic functions, which is really where the applications come in. But anyway, let's look at this first, and then we'll take a look at a video. So the way you do this is you make this substitution. So if you're interested, if you're into calc substitutions, you would make this substitution into the original series that I just showed a second ago to change a 2 pi periodic function into a 2L periodic function. So extending it to different sizes. And then if you do that, you get a new Fourier series approximation. And so what this is the exact same thing that I just showed a second ago. Maybe I should stop putting that away because I keep pulling it back out. Page 15, I think. or 14 actually. This is the exact same thing on page 14, just with some slight modifications. Like if you compare this to that, I'll point out the few differences, right? So instead of having like cosine nx sine nx, you've got nx times pi over L. So you've got a pi over L inside there now because you've made that substitution with the pi over L. Instead of going from minus pi to pi, you're integrating from minus L to L. Instead of having 1 over 2 pi or 1 over pi, you've got 1 over 2L, 1 over L. And then again, these things have the L in there as well. And so you're just extending. It's the same exact kind of idea, except this is how we can approximate functions using a Fourier series outside of minus pi to pi. So a Fourier series on any interval around the origin. But you just do the same kind of thing. You can still use the calculus trigs that we sort of brushed up on. You can still, you still have to like evaluate each one of these things. Then you just plug it into the formula. It's like the exact same thing. There's just different bounds, right? That's pretty much the only thing here. And so I'm just going to sort of remind you about how this works with one example, and then there might be time to try some of these on Maple. Let's see. So let's look at the Fourier series for the periodic extension of f of x equals x on minus 1, 1. And so we did a kind of a similar problem. I don't know if we used x or not, but the key thing that's different about this is the on minus 1 to 1 part. In other words, it's not minus pi to pi anymore. We're doing a different interval around the origin. And so remember how the periodic extension works is like you graph this thing on that interval and then you just copy and paste it to get different periods, right? And so let me do that down here. Let me draw the picture of what this looks like. So this picture goes from minus 1 to 1, and we're graphing f of x equals x, and so that the y values will also be minus 1 to 1, right? And so x from minus 1 to 1 does this. Right? That's the line y equals x between minus 1 and 1. And so that's one period, and so the periodic extension would be just copying that and pasting it down the line here, right? So like the next piece would go from 1 to 3, cross at 2, and it would do this kind of thing. It would go between those points. And then there'd be one going this direction too, right? There'd be one going down here as well, right? So that's just a periodic extension of that thing. You draw one, what you're being told, and then you just like copy and paste it on over. And it's helpful sometimes to draw the graph, or at least think about the graph, because if you have certain types of symmetry, we know that makes these integrals easier, right? And so we see that this one it has origin symmetry, right? Wow, that was horrible. This should cross at the origin. I just realized how bad that was. This should cross right here. That's what happens when you draw something by hand. It should cross right at 0. Anyway, it has got symmetry with respect to the origin, because if you turned it upside down, it would look the same. And so we know that helps some of our integrals. And so f of x is symmetric about the origin, which means that it's odd. And so that helps with integrals. Stop me if you need to. I'm just going to remind you how to do these integrals. Write down one of the examples, and then we'll sort of get a definition. And then I don't know if we'll get to this or not. Let's see. So we calculate these things, right? We calculate A0, AN, and BN. So I'm going to use these formulas right here down below. And so A0 is, right, L is 2 in this case. Maybe I should make that case. So L is the size of the interval. And so when you have 1 over, L is 1, I'm sorry. Because you're going from minus L to L. And so the L here is a 1, and so that's why you get a 1/2 out front to start. Anyway, so you integrate over the interval -1 to 1 of x dx. That's a really easy integral to do, but you don't have to actually do anything because we know it's odd, and so we know it's going to be 0, right? The area under the curve here balances with the area under curve there. So that just equals 0 because it's odd, and the same thing actually ends up happening with an. So an ends up being this integral. Oops, that should be +1. And so you have odd times even equals odd, and so you're also integrating an odd function, and so that also ends up being 0. So again, those little calculus tricks are really, really helpful in this case, right? So these are both equal 0 because the integral of an odd from -L to L is 0. And so we're only going to get a Bn term. And when you do Bn, here's what we get. So when we find the Bn coefficient, we again do 1/1. We're integrating from -1 to 1, and you do the function times sine n pi x. This is technically over 1, I guess, because L is 1. And so let's make this one a little bit easier and just go from 0 to 1. So we know that this is an odd times an odd, which is an even. And so we can cut this integral in half if we want and just go from 0 to 1 and multiply it by 2. This is why we looked at those calculus definitions. And then we would use, tabular integration on that. You could use tabular integration, I guess, on the first one too. I just wanted to have a 0 as the integrand because maybe it makes it a little bit easier when you do it. But when you use tabular integration, you'll get this. And then you need to evaluate that from 0 to 1. And when you evaluate that from 0 to 1, you get this. And we had already previously seen that when you do cosine of n pi, that oscillates between plus or minus 1. And so that's a fine way to write that, or you could write it like this if you wanted to get rid of the trig. Either one of those, like if you entered either one in Maple and tried to plot it, that'd be fine. And then we just plug the things in. And so we only get a Bn coefficient here, right? And so when we write down the answer, we're only going to get this one term in our answer because these two ended up being 0. And we'll define why that happens in just a page or so here. And so our final answer, our final Fourier approximation is the infinite series of 2 over n pi minus 1 to n plus 1. That's the Bn coefficient we just found. By sine n pi x. And that would provide a very nice approximation of that function. Let's pause here and let folks write stuff down, see if I can answer a question. The one that I'm going to ask folks to try, I hope this period is going to be a similar one, except we're going to look at minus pi. So it's going to be the same graph, except it'll be going the other way. But it'll be kind of similar results.
I had a quick question.
Yeah.
So why exactly is L 1? Is it because we're looking from 0 to 1?
Yeah, I got a little confused about that too. So so you're doing something symmetric around the origin, and so the size of it, so if this is the number line and you're 0, you're going from L to minus L.
Yeah.
And so the length of that is 2L. But the L itself is only half of that, right? Like the size of one of the, when you do plus or minus L, you're going like L on either side of the origin.
Okay, so you're
L
not looking at the
itself-
whole thing. You're just looking at like the one L.
Yeah, because you're doing like plus or minus that exactly. So it has period 2L, but in other words, like this one had period 2, but it's 2 times L, and so it's 2 times something equals 2, and so L is 1 in that case. And so
Okay.
maybe what you said was true. You just want to go like out just one side of the interval, and so it's going to be
So it's technically the same on the other side, just in.
yeah, it's like whatever's inside the interval you're given is L.
Okay.
That's another way to think about it, because this is always going to be like plus or minus some number, like plus or minus 3 or plus or minus pi, plus or minus 10, and so whatever is in there is L is the absolute value.
Okay.
Yep, thanks. Sorry about I definitely messed it up when I first said that. I got a little confused when I was reading that up top there myself. And so another maybe way to see that is, right, the integral goes from minus L to L, and so L is like the individual integral parts.
Okay.
Other thoughts, other questions I can clarify about that? Okay. All right. I think there's a blank page next. I think I had maybe anticipated this taking up more space, so I'm gonna just skip that next page since there's nothing there. And I want to skip this real quick here, actually. I'm going to reverse the order of the next 2 pages. So I'm going to first look at page 22, since it's more applicable to what we just did. And this is just really clarifying something that hopefully you've seen and realized what we've done so far. And then I'm going to look at this page next, because this will then take us into the activity. So what we've seen so far on some of these examples, like on the last one, we had an odd function, right? It had symmetry with respect to the origin. And what ended up happening is A0 and AN ended up being 0. And in a previous example, when we had an even function like this one, this is from last class, right? This was an even function. And when we found that Fourier series, the B ended up being 0. And so there's something going on there. And we saw that a couple times when we had these types of these different symmetries. And this page is sort of fleshing out what is going on with respect to how you know or when does AN or A0 become 0. And so this one here is it says the sine and cosine series, and it's telling us the Fourier series for an odd periodic extension. And then it's going to tell us the Fourier series for an even periodic extension. And so we already kind of know these things. We've seen these things in practice, but this is just sort of labeling it and again, fleshing it out. And so anytime we have an even function, this is going to end up being the Fourier series. In other words, where Bn is the integral we already know. In other words, i.e., if your function that you're approximating is odd, AN and A0 are both going to be 0. And so the resulting Fourier series is only going to have the Bn with the sine term in it. That's why it's called the sine series. And so if you have an odd function, you end up getting 2 zeros for 2 of your coefficients. And so that means the Fourier series will contain only the sine term. And so that's called the sine series, like it says. And so anytime you end up with an odd function, you kind of could just cut to the chase is what this is saying. There's nothing wrong with doing the integrals, and hopefully you'd find them being 0 anyway, and you would get to this point. But this is just sort of cutting to the chase and saying, hey, you're going to get a couple zeros in there anyway, so just this is what you're going to have to do. And then the opposite's true when we have an even function, right? So Bn was the only thing that was non-zero when we had an odd function. And when we have an even function, Bn is the only thing that is 0, right? And so if we have an even periodic function, we end up with only cosine in there because Bn is always going to be 0. So if f of x is even, then Bn is going to end up being 0. And so the Fourier series has only cosines. And so the larger definition still applies. These are just sort of saying, hey, if you've got an even function or an odd function, you're automatically just going to get sines or just going to get cosines. And if you see something referred to as the sine series or the cosine series, that's what they're talking about. It's really not, I don't think it's like a huge thing. It's just kind of pointing out what we've seen in some of the examples that we did. Okay. I like to spend the rest of the time showing you what an even and an odd expansion is, and then asking you to try to do a couple of those in Maple. So that's my plan here, if there aren't any questions about this particular page. All right. So this is just another definition, or a couple definitions. And I know it looks confusing, but it's actually not that bad if we just kind of look through it. So, so let's, in this particular case, we're talking about just the right-hand half of the period, so 0 to L. So we're looking like to the right of the origin, in other words, right? And then we're being told what the even periodic extension and the odd periodic extension are. And the types of questions you see for this are what's written down at the below here, like plot the even and the odd periodic extension of this graph. And so let's go through them one at a time and then apply it to this function. So what we want to do is plot the even and the odd periodic function of 1 minus x. And 1 minus x is currently being defined from 0 to 1. So let me draw that picture first, and then we'll go through each definition, and we will apply the definition one at a time. So 1 minus x is a straight line that has a y-intercept of 1 and a slope of -1. And so if we're going from 0 to 1, then it starts up here at 1, and it goes down to right here. Right, that's the line 1 minus x on 0, 1. Just let everyone write that down so then I can start pointing at things again. So let's read the definition. So the even periodic function says, we're going to calling the even periodic function capital F of x again. It's going to be the regular function on 0 to L. So like you copy this and just leave that alone, that piece. But then on the interval to the left of the origin, so from minus L to 0, you do F of minus x. And so this is just telling us to reflect the graph around the y-axis. And then the third part says, copy the rest of it every 2L units. And so if this is our graph, let's draw the even periodic extension. We would reflect this around the y-axis. So let's draw the graph we had, which was this. And then we reflect this around the y-axis. And so it'd be like just flipping that over, or you could think about like folding the thing like a book, and where would this line up? Well, it would line up over here. And so that's the periodic extension from -1 to 1. And then if you wanted to copy and paste it, like the full extension, the full periodic extension would just be copying and pasting that repeatedly. And so that would be -3. That would be -2. That would be 2. That would be 3. Is that okay? The odd periodic function, or excuse me, the odd periodic extension, like it says here, you again copy the graph on the normal interval, and then to the left of the origin, you do -f of -x. And so this is telling us to reflect around the origin. And so we take this one and we like flip it down here to make that happen. The other way to say that is you could turn this graph upside down, and wherever that ends up being would be the odd periodic extension. So the odd periodic extension of this function would be, first copy the graph normally from 0 to 1. And then imagine turning this upside down or flipping it around the origin, right? Let me just turn it upside down and see what that looks like. If I turn the paper upside down, now it's like down here in the fourth quadrant kind of thing, right? And so the odd periodic extension of this one then would be this. Should be a reflection. It's not quite looking like that, but hopefully you get that. And then if you copy, the interesting thing is if you copy and pasted that, like if you copied this line, this thing, and then you slid it over, this thing right here would line up with that. And so when you do the periodic extension, it's going to end up being like this. Which is kind of an interesting thing of that one. Questions about either one of those? So notice that this one is even, right? Because it's got symmetry with respect to the y-axis, and this one's odd because it's got origin symmetry. And so one of them, the odd one is going to end up being a sine series when we approximate it, and then the even one is going to end up being a cosine series because it's odd and even. So we're going to apply what we just learned on the last thing. And so that's what the next 2 pages are doing, right? It's saying find the sine series of this thing, and then find the cosine series of the thing. And that's what I was going to have folks work on for a minute. But in order to do that, and you can use Maple and everything, and so we can use Maple. But in order to do that, we need to define these functions, because that's what we need at the top of our Maple code. So let's define these functions. It equals something from -1 to 0, and it equals something else from 0 to 1. That shouldn't be there. And it'd be nice if someone could help me with that. What do you think about that? How do we define either one of these functions? It equals 2 separate things to the left of 0 and to the right.
So to the right of 0 would just be 1 minus x, right?
Yeah, right, exactly. I was going to say, so the one to the right of 0 is what we were given, right? And so that's to the right of 0 is just going to be 1 minus x, and both of them we were just given that. But let's look at this one. What is this line? What's the equation of that line? So it's got a y-intercept of 1, and it looks like maybe a slope of 1.
So that'd be x plus 1?
Yep, x plus 1, or 1 plus x. And then what about this one? This one probably also has a slope of -1, but the y-intercept is down at -1.
So just x minus 1?
Minus
or
x.
negative x minus 1, excuse me.
Yeah, right. And so when we go ahead and we do these Fourier approximations, remember in the Maple code, there's like at the top of the script, I would recommend using the one, I think Fourier series B or C. Oh, I resaved it as C. Fourier series B might be a good one to mess around with. So I'm going to switch over and show my screen. And I'm just trying to set this up, and then I was going to let people work on this for a couple minutes. Let's see here. How do I share my screen? And then I'm hoping to have folks share their screen and see what we can get. I've already got the answers up here in my cosine and sine series, but when you open up Fourier series B, it should look like this. I'm sharing my screen now, just to be clear. So you can check out my screen. Let me see, make sure my screen looks okay. Okay, yeah, it looks fine. So basically you can, you will have to change this one, that's right. So you will have to change it a little bit because you'll have to change the bounds and you have to change the integrands, but it's set up to mostly do the work. What the main thing you need to do is change the piecewise part, right? So you need to redefine the function correctly. You should change the interval and then just change the integrands. And that should do it. I mean, technically you don't need all of them because it's a sine and a cosine series, but you can calculate them, and some of them are just going to end up being 0. And then this is the full-on form, although you have to edit that a little bit too. But you should be able to approximate these things without too much of a problem just by changing this particular code. So I'd like folks to work on this. I feel like maybe 10 minutes would be a good amount of time or more. And I have answers written down. And so I will go ahead and scan and post my answers after this, including graphs and stuff like that. But if you want to take a second and try these yourself, that'd be good. I just think this is a good time, because the homework is all about this. It's all about like using Maple to do a Fourier series and then answering a question after you do that. And so I think this is a good time for you to try it while I'm here. And if you have a problem, you can share your screen and maybe we can work it out. So this is a good time to try that. So I'm gonna break for 10 minutes or so. I would ask you to try either page 23 or 24. If we were in class, I'd probably split them up and then have you present them and stuff like that. But for right now, just get your hands a little bit dirty on these and see if you can adjust this code to approximate either one of those things. If you got time, try them both. Can I clarify something about that?
Yeah, real quick. So when we're adjusting the code at the top, so like the pi's are going to become essentially -1 to 1,
yes,
to 0, and then so like where exactly do we put in like x plus 1 and 1 minus x? Is it just
that goes into the piecewise part? So you define the function up here. Right, so this is telling us between, so let me just do the first one. So let me do the which is the first page? The first page is the odd one, and so it'd be the sine series. So that would be like -1 to 0. Oops, I put minus. So -1 to 0. The function is.
Oh, okay, that's where the function goes. Okay.
Minus x minus 1, yeah. This is where you're defining it. And then from 0 to 1, the function is 1 minus x. And so when you do that and then graph it, you get that thing.
Okay, yeah, I just didn't understand how to put it into there, but now it makes sense. So
these bounds need to change too. I plotted this thing from -pi to pi. It should be from -1 to 1. So when you change that, this is more of the picture that we started with.
Oh, okay, yeah, that makes sense.
Other questions or thoughts about that? Again, I'm gonna sit here and maybe mess around with mine off screen. I'm gonna maybe stop sharing my screen for a second so I can, I won't need to do that. I'm just gonna pull mine over here. Can I do that? No, I can't do that. Anyway, I'm gonna sit here and let you work on that for a minute. I hope you do that. You can sit there and twiddle your thumbs if you want, but I think this is a good time to try something just in case you have any problems with it because I'm here. And then I will show my answers in say 10 or so minutes, and then we can go on our way. And if you have any problems, again, reach out. If you were in class, I'd walk over to you, but maybe you could share your screen and I could try to figure out if there was something I could help with. So I'm just going to sit here and work on mine for a minute while you guys work. And again, yeah, go ahead.
As you say, I'm just switching computers real quick because I don't have Maple on my big computer.
Sure. Yeah, does anyone have a problem with accessing Maple Home? I was assuming that everyone, I know everyone had it on their laptop when we were in class. Did anyone have a situation where they had to like give their laptop away or something? Does anyone have a problem getting on Maple? I guess is my question, because there's a lot of Maple in this next homework. Maybe I'll just start editing this one just so we can.
So when I tried to put in, like adjust the piecewise at the top, it doesn't. It's not doing it. I don't know.
What are you typing in there? Does it look like mine?
Yeah, so it looks exactly the same as that.
So then to actually run it, you need to click this exclamation mark.
Oh, okay. I thought I did the last time. I guess I didn't. Okay.
If you click the one that has all three, it'll run the entire page, and if you just click the one that has one, it'll just run the line, the single line. How do you do pi? I can't remember that. Remember that? Can you just type pi? You just type pi. And the fact I'm not getting an answer means I don't know if anyone's doing this. Oh gosh. Does anyone know how to do pi in Maple? I'm trying to look it up. Oh, it needs to be capitalized. Work. No.
I mean, there's like it's under common symbols on the left, but I don't know if that's like considered the actual thing.
Let's find out. I think it's just capital PI.
Right.
I did capital PI, hit enter, and it showed pi. I've got my first integral squared away. Let me get my second one squared away. And then this is doing 20 terms, and then let's go from -3 to 3. Oops, that's not right either, though. So I need nx times pi.
So L in this case is just 1.
L is still 1. Yet we're going on either side of the or what I meant to say was the interval is 0 to 1, so L is 1.
Okay, so like when we're doing for like the example, so find the sine series. So we're using the odd thing that we just had, and we're only doing it for Bn.
Yeah, right. So I just did it for all of them, and then they,
Oh, because then you just have them all.
They should end up being 0, basically. But I think I messed something up. Let me see here. So this is supposed to be the sine series. And so it should have just Bn. So this first one is not correct. What's wrong about this one here? Is that not working? Oh, there it goes, 0. Okay, I don't know why I said 1 over 2 pi before. There, that's much better. And so I just walked through that first one. If anyone had an issue with that, hopefully that was helpful. And this will be, you know, I'm recording this, so this will be on YouTube if you need it later. And then you can do a similar thing with the other one. And I'll just sort of wait a few minutes to see if there are questions about that, and then I'll show you that here. I'll go ahead and save these into the Dropbox, might as well.
So I just have, I guess, a question about Maple kind of code in general. So for like A0 and for the rest of them, so f of x is already in there. So where is that? So that's the 1 minus x.
Say that one more time. Yeah, right. F of x is defined at the top there. That's the piecewise part. So you just define one period of it, which we're plotting right here. So you're only defining one period.
Right.
But when you do the Fourier series, it extends the period in both directions.
Okay. Okay. But so at the top, when you're defining the piecewise, it's that the part after the last comma, that's technically the f of x, and the beginning part is just the period.
Yeah, right.
Okay.
This is the f of x, and this is the f of x. I think you might be able to switch the order there. I'm not actually sure. This piecewise thing is obviously a built-in function, and maybe it requires the interval first. I think that's what's going on there. It's been a while since I built that thing. But you do need to define an entire period, right? So we're only given the function from 0 to 1, but then we reflected it to get the other side, and then that becomes one period. Is sort of the idea.
Okay. Okay. Yeah, I see what you're saying. Because that's technically just the, where was it? That's technically just the odd periodic extension.
Correct. This is the odd periodic extension, which means that the answer is only going to have signs in it because the function is odd. Okay,
so then essentially we just do the same exact thing using the even, and that gives us the cosine series.
That's right. Yeah, it'd be the same exact thing. I actually already have it here. I'll just go ahead and show it to you. Is anyone still working? I don't know if people want more time. If people are just blowing us off, that's fine. But I'll give you more time if you want, or we can just move on here. Does anyone need some more time, or want to ask a question or something? And I'll just say again, like most of the homework for the next homework assignment that's not due for a couple weeks, but you should start looking at it. You can use Maple for most of those things, and I would recommend using these codes. So this would be the other one. This would be the even periodic extension, where we have an even function because we reflected it around the y-axis. And this isn't quite right. I don't know why this is doing that. This should be from -1 to 1, -1 to 1, -1 to 1. This one's all messed up, actually. I don't know this, and that's not right either. That should be 1/2. Should just be 1. And these also don't have the pi's. Oh, yes, it does. All right, let me see how that looks. Yeah, so then Bn becomes 0, and so then we only get the cosine terms. And then even just with 5 terms, it becomes a nice approximation. Let's just do 3 terms, or let's just do 2. Let's just do 1 term to see how coarse it looks. It already looks pretty good. Let's do. Is that really right? Oh, then I didn't need to plot it. I did plot it. Wow, so this one actually looks pretty good pretty quickly. I think as you start adding terms, though, those corners probably start to sharpen out. Yeah, see how the corners start to look more like a triangle. And when you use 100 terms, you really get a good approximation of that. And so I'm just going to sort of flash up the answers. This is what I have written down for this. And I'll scan this with the notes here. For the sine series, L is 1. Here's the work. You're only going to get the B function. And when you get a plot here, this is the plot. I just did a hand-drawn plot of that. And then when you do the other one, you only get the cosine terms. And so this is what you end up getting by hand, if you do it by hand. And then you end up approximating it kind of like that. So I'm just going to scan these things. I've also got some printouts from Maple that I will also scan. And how about I go ahead and save. I'll save all these things in the Dropbox if you think that would be helpful.
Yeah.
I think that would be good.
So
yeah, go ahead.
I was going to say, so when you're doing it in Maple, it's going to give you your coefficients, and then you still have to just go the one step to put it into the sum to find the actual Fourier series, or does Maple actually give you the?
So the sum is part of that Maple code. So let me just show you.
That's that end piece where
If you look at the bottom of the very bottom of the code, it's got the series right there. If I'm sharing my screen again, you know, the series itself is right here. I'm highlighting it. And so you calculate the A0, AN, and BN right here, and then they go in here, and then you plot it.
Okay. So we're writing it out as an answer. We would just plug in all the coefficients that we got right above it.
Yeah, that's right. Yeah, so you would plug in 0, 0, and then 2 over n pi. Right.
Okay. Cool.
That's right. So yeah, again, I will. I've already saved. Right? I don't know. Maybe I didn't save that one yet, but I will save all of these into the Dropbox, and I'm around. I'm around to help. Don't wait too long on this. If this makes sense, like I think you should just do some of the homework so you can have before you lose. You know, before you forget about what you did and how to run the Maple code. Basically, it can be a very easy homework. I guess is what I'm trying to say. If this makes sense, and you just kind of do it sooner than later. But anyway, that's all I really got. I'm going to go ahead and save these in the Dropbox right now. And if there aren't any other questions, we'll just see you guys on Tuesday. And please don't forget to submit your homework.
I have a few homework questions, I guess, if I can just stick around.
Sure. Hold on one second. Let me save these.
Yeah.
These are also... I'm going to keep recording just so I can post these homework help answers maybe.
Okay.
Can I ask something else about number 4?
Yep.
So I kind of already forgot. When n doesn't equal m, you can't like solve for m or n, right? Is everything?
So when m doesn't equal n, then none of those terms go away, right?
So just all be 0?
So they would all be 0. And you want that to, right? The answer is 0 when n doesn't equal m.
So do I have to show anything, or can I just write that they all equal 0?
You can say by lemma 5.1, all these integrals equal 0.
Okay. Do I have to like show each integral individually, or can I write it as just one?
You can just reference lemma 5.1, and I'll know what you're doing there.
Right, but do I need to have 4 different integrals or just one big one?
Just one's fine.
Okay. All right. That's cool.
Danny?
So yeah, so I was working on part of it. Like number 4 makes a lot more sense now. So I need to go just kind of write it up after we talk about it. For the first one, I was just trying to wrap my head around, like, so we have f being odd, right? So it says if prove if f of x is odd, then the f prime, so the derivative is even.
Yes.
So I was trying to figure out like how to show that. So like I started out with like f of minus x is equal to minus f of x, right? Yeah.
Yep.
So then from there, I guess, what do I like? Because I was looking at the proof for like the lemma. I think it was going the other way.
Yeah.
And I just wasn't really sure, like, I don't know, I guess where to really start with it, to be honest.
So it's like a chain rule thing. So
okay.
So if f prime is even, what we're trying to show here, we want to show that f prime of minus x equals f prime of x. And so we can start with what we're given here, take the derivative of this, which will give us primes, and then hopefully it'll result in this. That's the idea. And so you can do this, and then just differentiate both sides. Well, maybe that's not exactly. Let's just start with f of minus x.
Okay. So like taking the, so like, okay.
Okay, here's what we're going to do. There's a couple different ways we can think about this.
Okay.
So this thing, f of x being odd, also means that this is true.
Right.
So I think that's actually what we want to start with.
Okay.
So let's take the derivative of the function. Well, we just said that the function can be written like minus f of minus x. So this is the same thing as taking the derivative of this. And this first thing is f prime, right? So this is like, and so hopefully at the end of this we have this, right? So we hopefully have f prime of minus x somewhere at the end of this.
Okay.
And so this is kind of a tricky part. I did this one in class previously, and I've been talking to people online a little bit about this particular one. But when you do a derivative like this, it's really the same thing as this. You can just pull the -1 out, for example, to start. But then when you have like the derivative of a function with something plugged into it, that's where you use the chain rule. And so this becomes minus the derivative of the inside piece times the derivative of the outside piece. That's like the definition of the chain rule. It says when you have a function with something inside of it, you take the derivative of the outside function, but then you multiply it by the derivative of whatever's inside.
Okay. Oh, okay, right. So it's like, okay.
And so this ends up being -1. Right, so you have minus f prime of -x, which is f prime of -x. So we just showed that f prime of x equals f prime of -x, which is the definition of being even.
Okay.
That one was particularly tricky, and again, I usually wait for sorry, I just got a text. It's funny how, because some reason I would never like be talking to you in person and suddenly text with them for some reason, because you can't see me. Like, well, I'm just gonna go ahead and do that. Anyway, I know that one's a hard one, and I usually do that one in class, like I said. And there's also other ways to do it. You could use the definition of a derivative, which is what I was talking to Bradley about this, and she did it a really interesting way where she used this definition, and she got a nice answer out of it. And so that's sort of another approach.
Okay.
And this might make more sense to you if you don't remember the chain rule, for example, but either one of those is fine.
Okay. Yeah, I kind of wrote up that one as we were doing it.
That's fine. No problem.
So 3 made sense from just doing it in notes. So for 2, I guess also, so I try to do it similar to the one that we did in the notes. I don't know if that's technically how we were supposed to do it though.
I think so. Was that on page? Do you know what page it's on? I think I know what you're talking about.
On page 8, we did it for proving it equaling 0. So since we got like a GA minus GA. So in this one, I think I did it similar, and I ended up getting like a GA plus a GA.
Yes.
So it's just 2G of A.
2G of A.
Okay.
Right. And so then 2G of A equals 2 times the integral from 0 to A of little f of x.
Yeah. Okay. Cool. So that's what I did for that.
Correct.
Okay. Cool. So I'm just gonna do the number 4. And that one, we're pretty much just showing when the things are 0 and when they're not, and then how that equals it.
Correct. Yeah, that's right.
Okay, awesome.
It's like number 4 is like a really scary, hard-looking problem that actually is very easy when you just like reference the lemma.
Right. So and the lemma was on page, was it 2?
It's 5.1 in the textbook, and it's on page 2 of the notes. Yeah.
Okay. Awesome. Cool. Yeah, I think that's it. Then I'll, like I said, I'll write the last one up and then scan it.
Okay. All right. Great.
Thank you.
Take care.
You too.